Good morning, everyone. Good morning, Professor Rechberger. Welcome to the Tassiszaal here in the heart of the University of Antwerp and also in the heart of the city of Antwerp for the conferral of one of the honorary degrees for 2022. My name is Anke, I'll be your hostess this morning in this beautiful location, and I'm grateful and delighted to be surrounded by so much knowledge, hard work, and incredible talent. Honorary Dr. Helmut Rechberger will shortly be teaching a masterclass titled Anthropogenic Metabolism Seen Through the Lens of Entropy. During the masterclass, you can ask questions using the chat function on the YouTube channel. This is for the people who are watching online. And after the masterclass, there will be time for a Q&A session in which Professor Rechberger will answer the questions you submitted. Then we will proceed to the conferral of the honorary degree. But first, I would like to give the floor to Professor Tom Breugelmans, Dean of the Faculty of Applied Engineering, who will offer you all a warm welcome.
Dear Professor Rechberger, Rector, Vice Rector, dear professors, colleagues, dear Mrs. Rechberger, and hopefully also family and relatives of Professor Rechberger online, ladies and gentlemen, as Dean of the Faculty of Applied Engineering at our University of Antwerp, it is an honor and a real pleasure for me to be able to welcome you all today to the masterclass and to the official ceremony of the honorary degree to Professor Helmut Rechberger. I speak on behalf of the entire faculty when I say that I'm also delighted that the still somewhat different circumstances did not prevent you from attending this event, and that we have a lot of colleagues also listening online to the masterclass in a few minutes. An honorary doctorate allows the faculty to honor an exceptional researcher and also to highlight important research. For our faculty, this is now the third time that we have the opportunity to award an honorary doctorate. In 2017, the spotlight was on electronics with the honorary doctorate to Professor Jan Rabai. In 2019, the numerous possibilities of infrared thermography were the theme of the honorary doctorate for Professor Xavier Maldage. Today is the turn of our chemical engineering department. This time we have opted for research that focuses on sustainability, a theme that is more relevant than ever. It is important for our engineering faculty to take part in the social debate on sustainability, and also through these initiatives for our students and the future engineers to understand the importance of their technological skills as part of a solution for creating a more sustainable society. An honorary degree is also a good opportunity to focus on the importance of international collaboration and networking. Today's challenges have an impact on the whole world. This is certainly also the case for environment, climate, and sustainability. To find answers, international cooperation is more important than ever. I am therefore very pleased that we are able to welcome Professor Helmut Rechberger. He is very known for his research on ecology, recycling, waste management, and various related topics. For this reason, I would also like to express my appreciation to the faculty supervisor of the honorary doctorate, Professor Peter Billen. I am convinced that we are going to have a very interesting event and hope that you will all enjoy the masterclass. For information about Professor Rechberger's career and research, I would like to give the floor to Professor Peter Billen.
Thank you. Dear Professor Rechberger, dear Rector, Vice Rector, dear colleagues, dear Mr. Dean, dear friends, family of Professor Rechberger and the like, dear students, ladies and gentlemen. Imagine a time when we made more and more highly technological products which tremendously increased our societal welfare. They were made from a diversity of materials, and when these products did their job, we threw them away in a dump, typically, or at best we just burned them. This was not that long ago. In a time where recycling businesses were taking baby steps, while some countries, including Belgium for instance, were championing the separate collection of waste to burn it afterwards anyways, Professor Rechberger already realized that you cannot manage materials optimally if you're not able to map material flows. In such case, you would be driving blindly. Together with his doctoral advisor, Professor Brunner, who is also here today, welcome, he published a widely used book on material flow analysis that allows companies, governments, researchers, and innovators to discover opportunities for improving the sustainability of materials, and set in motion also the transition towards a circular economy, even before this became a coined term. Moreover, Professor Rechberger also realized that our problem is not so much the scarcity of resources, but rather their dilution and our ability to utilize them. The methodologies derived from this observation led to novel guiding principles to actually establish a circular economy. Not only can we now map out and quantify material flows, we also have the tools and metrics to evaluate their intrinsic circularity based on solid thermodynamic principles. Professor Rechberger is full professor and head of the Institute of Water Quality and Resources Management at the Technical University of Vienna in Austria. He holds a doctorate in anthropogenic metabolism and waste technology from the same university, but also did research in the past at ETH in Zurich and at Yale University. It is thus my honor to introduce the masterclass of Professor Rechberger, in which he will take us back to the roots of smart materials management, namely the second law of thermodynamics. Professor Rechberger, the floor is yours.
Rector, Vice Rector, Dean, Peter, colleagues and friends, it's really a pleasure to be here and have the opportunity to give this masterclass today. And I selected a metric or topic that accompanies me whole my academic career, or even longer, because already as a student I liked thermodynamics, and especially the second law of thermodynamics, the entropy law, was very interesting for me, because entropy is an interesting metric. It's not arbitrary, it's not ambiguous, it always points into the same direction. So you can really rely on entropy, it's robust, it always shows you what's wrong or what's good. On the other side of the coin, it's not a positive value. We have to avoid entropy. We have to keep it low. And it tends to become always more and more. And at the end, it's the point of rien ne va plus, or game is over, which is not so positive. But I'm quite sure that it's a good metric for analyzing and understanding the anthropogenic metabolism. And this is what I would like to show today. First, I would like to say something about metabolism. The first ones who investigated metabolic studies were physicians, medical doctors, and it's said that the first one was Santorio Santori. He was a contemporary of Galileo Galilei and also a friend of him. And he was a medical doctor, and his question was, I'm a grown-up man having constant weight, and he is consuming food and drinks, and he is producing some remainings, like urea, feces, and he thought this should be balanced. So he measured the amount of food and drinks and also his remainings, and then he was surprised because the input didn't match the output. So he thought something has to happen during night when he's sleeping. So he put himself into an animal hide, just collecting a few drops of sweat. He couldn't explain the difference. And in those days, Santorio, he didn't understand that inhale is something different from exhale. He didn't know about oxidation processes, so he could not solve the mystery. But this is more or less the same what we are doing with the metabolism of industrial economies. So we are using material flow analysis that has been developed in the 1980s in Switzerland by Peter Bacini, Paul Bronner. We are using a software that has been developed at our institute, and we are able now to analyze the metabolism of complex systems. Like here you see the phosphorus household of Austria, where you see the top layer. This is the most aggregated way to display this model. And such processes, these boxes, they can be split up to sub-processes, and sub-processes can be split up again into sub-processes. And such systems can become quite complex. In this case, we have more than 50 different processes and hundreds of flows. And this is where we start to investigate the metabolism of an economy like a patient. And we can do this, for example, we can investigate single flows. Like here, the application of mineral fertilizer to agricultural soil. We are developing time series, and we see that fertilization decreased over the years. We can also fix target values. In this special case, it would be that there is no over-fertilization of agricultural soil in Austria, and we can see how a single flow behaves. Does it go into the right direction, yes or no? The next thing would be that we investigate processes. Like you see here, the waste management process or waste management system in Austria. The input of phosphorus increased over the years. The output of recovered phosphorus stayed more or less the same. This means that the recycling efficiency of the waste management system decreased over the time. So waste management became more ineffective. And of course, this is then a need for action. We can also see what are the reasons for this loss of efficiency. For example, here you can see that phosphorus is lost to concrete and to landfills because sewage sludge, meat and bone meal is incinerated in cement kilns, and then it's finally in the concrete where it's lost forever, or it is landfills where it's also lost forever. So such studies directly point to the point of action, so they tell you what you have to do. And finally, we have the total patient, where we see the diseases of our, let's say, of our Austrian phosphorus household. We have not the time now to discuss this, but we can analyze these things step by step. Now I would like to come to MFA, material flow analysis, and I would like to start with an incinerator. And the reason why we are performing MFA for such facilities is that we are interested in the materials turnover that we see in such an incinerator. For example, this would be the total mass balance, where you see for 1 ton of municipal solid waste that is incinerated, we need roughly 4 tons of air. We need some auxiliary materials. We would produce roughly 5 tons of off-gas and several residuals. But we are even more interested in certain substances that are contained in the residual waste. Here you would see the example of cadmium. All the cadmium enters the process via municipal solid waste, and then it's distributed among several output streams. So we find some cadmium in the fly ash, and we are happy about that because finally the fly ash is stored in underground disposal facilities. It's safely stored there. We have also some cadmium in the iron scrap, where we would not like to have it really, because the iron scrap goes back in the metal, in the steel industry, where you don't want to have cadmium. So these are ways that we see how a waste treatment facility directs different substances. The same information that you have seen in the slide before is given here in so-called mass flow and concentration diagrams. So we would see here again the mass flows of the input streams. We see that the cadmium is only contained in the municipal solid waste. It has around 15 milligrams there per kilogram, and it's transformed into an output distribution where we see that the masses of the outputs are smaller than from the inputs, and we have some concentration effects. So in the filter cake, for example, we find roughly 350 milligrams of cadmium per kilogram. What would be the worst case for an incinerator with respect to cadmium? The worst case would be if all the cadmium is evenly distributed among the output streams, because then you have no concentration. In this case, it would mean that more or less all the cadmium would be in the off gas, and then you have it in the atmosphere. So this would be the worst case. And now it's time to introduce statistical entropy. In statistics, entropy is used to quantify distributions. And you can apply statistical entropy also to such types of distributions. And if you apply it exactly to this type of a distribution, you would find out that the statistical entropy becomes maximum. So it's a function of mass flows, given here, and of concentrations. And the analogy is in information theory, statistical entropy is applied to probabilities, to probability distributions. And concentrations and mass flows can be interpreted as probabilities. If the concentration is high, then you have a high probability that you will find the substance in this material. If the mass flow is high, you have also a high probability to find something. So this is the analogy. The best case of an incinerator with respect to cadmium would be if there is no cadmium in the output flows and there is only one pure cadmium cube dropping out at the end of the incinerator from time to time. Because then you have the cadmium concentrated, you can use it or landfill it safely, but it's under control. This would be the best thing. And for such a distribution, statistical entropy would result in zero. And for the real system, where we calculate the so-called relative statistical entropies, so they are normalized to the maximum, we would see that the input distribution results in 0.34 and the output distribution results in a smaller entropy value. This means that with respect to cadmium, the incinerator is a concentrating process. And just as a repetition, so how we apply statistical entropy to MFAs, if we perform an MFA for a process, we have the input distribution, we have the output distribution. We calculate the statistical entropies and then we compare them. And if the entropy becomes larger, so you have an entropy increase, this would mean that this is totally seen a dilution process. And if the entropy is reduced, then we have totally seen a concentrating process. Now, I would like to expand the concept to systems where we have several processes. So I would like to start with the copper, with the life cycle of copper, which can be illustrated as a process chain of 4 processes. So we start with the ore, and out of the ore we produce semi-products like cable, like slab or sheet, made of pure copper, more or less. And out of these semi-products, we produce products where copper is merged with other materials. After use, these products become waste, and waste management finally is hopefully able to recover some of the copper and recycle it back. And this would be the the MFA system for the global copper use, so where we see this process chain here, the copper ore that is processed, producing pure cathode copper, producing some wastes, tailings and slag from production processes, production of goods and so on. Such an MFA diagram can be transformed in such a so-called stage diagram. So this means that the ore is split up into cathode and tailings and slag, and we move forward stage by stage. And for each of these stages, we can produce such a mass flow and concentration diagram as I had shown before. In this case, we produce a large amount of tailings with a small copper concentration, a small amount of slag with a bit higher, with a bit more copper, and we produce a small amount of pure cathode copper. And for this distribution, we are able, again, to calculate the statistical entropy. And we follow the system from the left to the right, and for this stage 3, the cathode copper is then split up into copper-containing products or alloys, or also new scrap, of course, is produced during production. Again, we calculate the statistical entropy, and so we can produce or calculate the trend of statistical entropy along this life cycle of copper. So we follow now 1 unit of copper, let's say 1 kilogram of copper. And there are 2 extreme situations that we can have. Again, we can have this copper in our hands, completely pure, 100% copper. Then we have it under control and we can use it. This would be the situation of having 0 entropy. We can grind this copper to a fine dust and just emit it over the globe, so dilute it maximally. This would be the maximum situation here. And this is the calculated copper trend for our global copper use. So we start here with an average entropy with the ore. Then we reduce the entropy. We put a lot of energy into the system to produce pure semi-products. We are not here on the bottom because this process does not perform 100% efficiently. So we have tailings, we have slag, which are losses. Then we produce, again, entropy because we're mixing copper with other materials to produce products. Then finally, we have the most mixed stadium, the wastes, and the waste management system reduces the entropy a bit because copper is separately collected and recycled. The general, or the total copper trend it's quite interesting, is rather balanced. So at the end, we have the same entropy situation as in the beginning. If we analyze the single points here, it's interesting to see that around 1900, this dot here was around here, because the copper ores that were processed in around 1900 had much higher copper concentrations. They had a better quality than what we find nowadays. So this point or dot here constantly moves upwards. This dot here stayed more or less in this area because our technologies become more efficient. So we were able to produce the same amounts of refined copper from ore that is of less quality. So this stayed more or less the same. Here, this dot here is a question of, I would say, product design. So the tendency is nowadays that this dot goes upwards because our products become more complex. There's a general situation that we see. Product design could, of course, help to keep this dot in the bottom area. Then we have waste management. The better we collect things, the more efficient our waste management is, the more, or let's say, this would be a chance to keep this dot also low. But at the end, what we really need is the final dot should be somewhere in this region, because then we can speak about a circular economy, because we are interested in semi-products. We are not interested in ores. So we are interested in this kind of products. So we need a really efficient waste management at the back end. And this is one of my main messages I usually have. If we want to have circular economy, we need a technologically sophisticated waste management system. If you analyze the transition from here to here, there are many technologies behind that. It's not so easy to produce a pure copper cable out of ore. So there are different technologies behind that. And I think similar technologies we have also to develop here. Some of these technologies are already at hand, but we are not at this situation at the moment. Good. Here you see just, I would like to illustrate that the difference between copper and zinc. So both systems here on the global level look very similar. If we compare the entropy trends, we see that there is a significant difference between our use of copper and zinc. If we compare the overall entropy trends, we see that we are using zinc much more dissipative as compared to copper. And we know that galvanized steel, zinc is also used in chemicals as a nutrient and so on. So we have many dissipative uses. So entropy gives a good, I think, understanding of our quality of uses. Okay, this was a very simple example what I showed you for didactical reasons. We can also apply this to really complex systems. It's labor intensive, but if we're coming back to our phosphorus household, as I said before, more than 50 processes. Also such a complex system can be translated into such a stage diagram, and we are able to calculate the entropy trends. The phosphorus trend looks quite different from the entropy trend, so it's just going upwards. So we see that we are using phosphorus in a dissipative way. We can follow this trend over years. So the dotted line is the trend of 2000. The black line now is 2010. So we see that our phosphorus household in Austria become better. So we improved it. But even if we apply certain measures to optimize it, hypothetically, so we detected 15 measures how to improve this by technology, by different farming practice, by different diets of people and so on. Even then we see that we could not achieve a balanced entropy trend. So far, I talked about conservative substances like cadmium, copper, phosphorus. But quite often, the chemical speciation of an element is important. So if you consider nitrogen, for example, it makes a big difference if nitrogen is emitted to the atmosphere as molecular nitrogen or nitrous nitrogen, ammonium, or nitrate oxide. So there are differences, of course. And here you see two farming regions in Austria. The left one, the Vulca region, is a plant-based region. So mainly plants are produced in this region. And the right one, mainly animal products are produced. And both systems are normalized to 1 kilogram of anthropogenic nitrogen input. And what you can see is, especially here, emissions to the atmosphere are, of course, quite different if we compare. such a plant-based and an animal-based region. And this would be the result of the entropy analysis. The entropies of the inputs are more or less the same into the system. The output entropies are considerably different, and we see that especially the emissions of the animal-based region into the atmosphere produce a lot of entropy. There is also maybe a connex between entropy and toxicity. We are again back with our incinerator, and we now imagine we have an incinerator where we can turn on, turn off the air pollution control device, so from 0 to 100%. So this would be the entropy result that we get if we do this. So if the APC system, the air pollution control system, works 100% perfect, we would be somewhere here, and then we turn off the pollution control device, and at some point the entropies will go upwards. So we see here the entropies for cadmium and for lead. The two curves are different because we have more lead in the solid waste than cadmium. It's also we have tendency is that we have more lead in the ash on the slag than cadmium and so on, but that's not the point. So we see at some points entropy becomes significant, we see raises, and the interesting thing is that the areas where entropy becomes significant is exactly there where we find the threshold values, the emission limits given in the Austrian Clean Air Act. So this is, of course, no proof, no scientific proof that there is a connex between the entropy and toxicity, but at least it's a hint. And I'm quite sure that entropy is, in many cases, a good indicator also for toxicity, for environmental impacts. Another topic is recycling. It has been mentioned earlier. The European Union increases the recycling targets, especially for plastic waste, for plastic packaging waste. And if more of this waste have to be collected, we can assume that maybe the quality of this collected waste will go down. If you collect more, usually you enter a quality problem. And here I would like to show you very simple examples. We compare two sorting processes. They are sorting plastics, and the goal of this process is that one polymer type, PET, should be separated from the mixed plastic stream that enters the sorting process. And in this case, we would see that the total mass balances of these two processes, they are identical, but there is a difference with respect to the separation of PET bottles. So the right process is more efficient, able to target or to control or to transfer more PET bottles into the target stream. So we see the input concentrations for PET, of course, are identical, and we see that the process number 2 achieves a higher PET concentration in the target stream and a lower PET concentration in the waste stream. If we apply the classical definition of a recycling rate, this would be the same for both processes. Both processes achieve 70%. If we consider the quality with respect to PET, we would see that there is a significant difference with respect to their recycling efficiency. And of course, I didn't tell that, behind this effectiveness here, again, statistical entropy is the basis for this indicator. The same situation, but the other way around. So here, recycling process achieves a larger amount of the target material. This would be the PET balances, and what we see in this case is that the conventional recycling rate would see a difference, but we choose the numbers here so that the real recycling effectiveness is the same. Why is it the same? Because here, the consideration number 1, this is an advantage, but here this process number 1 loses a lot of PET in the waste stream, which is of course a disadvantage. So altogether, both processes perform equal in this case. And a last example, if the inputs are not identical, which is of course difficult because then you have no functional unit, you compare apples and oranges. But in this case, we would have again the same recycling efficiency, but the conventional recycling rate would be the same. But with respect to effectiveness, again, we see a significant difference. Now we come to systems where we do not have only one material or one substance, but we have many substances, like a mobile phone, which consists, more or less half of the periodic table, so 50, 60 different substances. It consists of components and subcomponents that can be separated, maybe not separated. And I wanted to show this example to show that statistical entropy can also be applied to systems or models where you have many materials, not only one. And in this case, we would see if such a mobile phone cannot be disassembled into different parts, we would have an average statistical entropy, in this case expressed as a product inherent recyclability. And if we are able to dismantle this smartphone step by step, and if we are also able to dismantle components into subcomponents or so if it can really be dismantled, then the recyclability increases. So this would be a metric that can be used by designers of a product. So they immediately get a metric or number that tells them how well recyclable is their product if they design it in this way. And of course, this had a lot to do with, can components separated into subcomponents? Is it glued together, or is it just a mechanical solvable link? And this is, of course, important for recycling. And it is only a metric that considers the product inherent recyclability. So it does not consider what happens afterwards with the smartphone. Maybe it goes into a very sophisticated recycling technology, or it's not recycled at all. So it's just a focus on the product itself. A few words about recent developments of statistical entropy. Entropy is not a standalone metric. It has to be combined. It has to be inserted into existing environmental, techno-economic assessment tools. And Peter Biln and Philippe Nimekas, they did a very nice study, I think, because they really showed how statistical entropy can be combined with energy, for example. So in my opinion, I conceive entropy as a gain or a benefit, something what you achieve, but you need effort for that. And effort can be energy, effort can also be costs, for example. And so they invented really a very nice way how to combine it with energy that is required for sorting different material streams, for example, or to combine it with costs and to show which technologies have the best effectiveness with regard to costs, how much entropy reduction you get for investing €1, for example. So this is some very nice research showing how entropy should be used, let's say, in practice. Oh, back. Good. I spoiled my message. Because, yeah, at the end of my talk, I wanted to become a bit private or philosophical. Because when I realized that MFAs can be interpreted as a transition of distributions, I started to see more or less distributions behind everything. And each problem that you spot can be translated into a distribution somehow. So is it the distribution of wealth, distribution of income, distribution of age, distribution of diseases, or geographical distributions, you name it. So I started to think always about which parameters do I have to select, what is the distribution. And so it took not too long that I came to an area which is quite close to me, namely classical music. And I show you one example here. These are two German composers, Robert Schumann and Franz Lachner. Both composed several string quartets, and I selected two string quartets that were composed more or less in the same time. String quartet number 6 by Lachner, and the first one by Robert Schumann. And of course, you can also produce distributions here. For example, distributions of single musical notes, distributions of keys, distributions of key changes, distribution of harmonics, of rhythm, whatever. But if you consider these distributions entropy-wise, they do not make a difference. But history has decided, or mankind has decided, I mean, the Schumann quartet has been performed, I don't know, 100 times or 1,000 times on stage. There are dozens of recordings. The Lachner quartet is hardly performed. The Schumann is really great music. I can tell you because I played both quartets. The Lachner is just good craftsmanship, I would say. So somehow I thought maybe entropy ends where art begins. And for me this was kind of a relief, because now I know entropy is not everything. It cannot explain everything in life, but nevertheless I think it's a very good tool to analyze anthropogenic metabolic systems. So as now I come to my conclusion, to my outlook, entropy I think is a good concept to analyze this metabolism. It helps us to understand it much better. And the strength is, I think it considers also the quality of resource use, and it also considers environmental impact. So it combines both. And I'm quite positive about the history, or the future of entropy. At least in Austria, we have a very new Kreislaufwirtschaft strategy, circular economy strategy. And on page 40 of this strategy, entropy is named explicitly. And the Austrian government, they are dedicated that entropy should be used as an indicator for monitoring of the circular economy. At least now they have to become operative, so they have to do something about that, as long as if they write it in such a strategy. And the other thing is, what makes me even more happy about the entropy future is that we are a growing community. And also with the help of this university, of Peter and Philippe and other colleagues, there is a growing entropy family, and I'm quite sure that we will see more entropy applications in the future. And this is what makes me very happy. Thank you very much for your attention.
Thank you very much, Professor Rechberger, for the very interesting talk. It was very enlightening for me. Here I received some questions from the audience which was following at home, so I will kindly ask these to you. Of course, if there are questions from the audience, please raise your hand, and Wouter with the microphone will pass by and so that you can ask your question. So maybe a first one coming from the people following online. Where did the inspiration come from to use entropy as a quantifying tool for material distribution?
Yeah, I think I indicated it somehow. Entropy was always fascinating for me. The inspiration came also a little bit by chance, I have to say, because I realized, at some point I realized that I need something that quantifies distributions. Mm-hmm. So this was the first step towards entropy. So I looked up statistical books for distribution metrics. And then suddenly I found in one of the statistical books, I found the notion of entropy, which I did not know that this is part of statistics. For me, this was kind of a good accident. Mm-hmm. And so I knew this might be a way to introduce entropy into the anthropogenic metabolism, because entropy has been mentioned several times. I mean, you know it, Stumm, Davis, they had a very nice entropy chart, but of course, Francesco Roegen and people like this used entropy all the time to describe the economic process as something that uses low entropy materials, turning them into high entropy materials and so on. But it could not be quantified. And this was, I think, the good thing about statistical entropy, that now we have something at hand that allows us to quantify things.
Okay, thank you very much. Maybe a question from the audience in the room? Someone in the room? Okay, I have other questions also summarized here, of course. What do you see as currently the biggest limitation for reaching a circular economy? What do you see as the biggest bottlenecks in waste management?
That's a difficult question. I mean, something what really concerns me is that we have this tendency, I mentioned it before, that our products become more and more complex with respect to chemical composition. And the more complex a product is, the more difficult it is at the end to recycle it. And we are nowadays discussing, for example, recycling of textiles, because our recycling rates for textiles in Europe are really low. But if you really go into the technical issues, you see that these mixtures of different textile types is very difficult for each recycling. And also, if you consider plastics, you have shown it in your work. If you combine different polymer types, this makes it extremely difficult for a good and qualitative recycling. So, on the other hand, I have to say I like my jeans, and they are a mixture of cotton and some, I don't know, some artificial textiles, and you can stretch them and so on. Yeah, but for recycling, it's not a good issue. So I think design of products is very important, and we have to try to produce the services that products should deliver in a more simple way if we talk about material compositions. And it's not only the case for a mobile phone or a jeans, it's also the case for buildings, for example.
All right, thank you very much. Maybe someone from the audience now, or yeah, okay, Tom. Yeah.
Thank you. Is it on? Can you hear me?
Yes,
okay.
it's on.
Thank you for your very interesting masterclass. Many years I lectured a course that had as name mass balances and energy balances. And I think it was also mentioned in the last slides, because if you want to close the loop and if you fully want to go to a circular economy, then the energy input is also very important. And this energy input, I guess, it's not a linear trend. The more that you want to lower the energy, certainly the last part to close the loop will probably ask much more energy than the first steps. So is there a kind of trade-off? Because if you look to a sustainable society, then we also want to do this completely with only sustainable and renewable energy. So is there a trade-off in which we say, what do you prefer? Closing completely the entropy loop, or having maybe less energy needed to go to, not to the last part of the...
Yeah, thank you. This is a very good question. I mean, I could answer maybe half an hour. The thing is to realize a circular economy is not a goal. It's just a means. So this is what I learned from Paul Brunner. Goals are conservation of resources, protection of human health and the environment. So circular economy is just a means to achieve these ecological goals. And for me, it's quite clear that if we translate circular economy into certain recycling rates, that it depends on the waste stream that you are looking at, but recycling rates maybe between 50% and 70 or 80% are the optimum. But after, I would say, if it's more than 80% for the most material flows, you come into this region that you mentioned where you need a lot of energy in order to close the cycle more and more. And this is something what I miss a little bit in the political and public discussion, because it always goes into the direction that they say we need higher recycling goals. And by just raising the recycling goals, they think they are doing something good. And this, maybe it's good, yeah, but it can be also counterproductive if you are already above the optimum. And for example, for plastics, I'm quite sure, I think for plastics, the optimal recycling rate is probably, I don't know it, because nobody has calculated it so far, at least as I know. I would say maybe it's between 30 and 50%, and it's never 70 or 80% that we achieve maybe for paper or for glass bottles, yeah? So it's very important, I think, to better understand the combination of the material flows and the energy flows, and we have to look for the optimal recycling rates. And this is a very difficult thing. The optimal recycling rate is a moving target. It changes all the time because the products change with respect to material composition, as I said before. Unfortunately, they become more and more complex. But also technologies change, prices change. So everything changes. So I would say an optimal recycling rate of today, maybe in 5 years, it's no longer the optimum. So and this is what we should more, I think, yeah, I think the politicians should more ask the scientists, where is the optimum? This is what I would like to hear more often, because I've never asked before.
Behind.
Thank you for a very interesting masterclass. I have one question on the recyclability of phones that you showed and the use of statistical entropy there. Can you use a statistical entropy concept to also differentiate between, let's say, a smartphone who uses screws and who's like modular and you can take out in different pieces manually, and one that it's like completely glued so you cannot manually dismantle it, and yeah, I don't even know if you can even dismantle it with technology?
Yeah, thank you. This is exactly what we wanted to show with this smartphone example, that the kind of connections between different components is, of course, decisive for the recycling gain at the end. And yes, this is exactly what we can calculate with the statistical entropy, because to make it simple, if two things cannot be separated, we consider them like one thing, entropy-wise. So, and of course, if you mix something, the entropy always increases, or if you combine something. If you can split it, and it has different material compositions, then the entropy is reduced. And this is the effect that is considered in this recyclability indicator.
Okay, maybe another question from the people online. I will summarize it a bit because that's a long question. Well, you mentioned toxicity before in your research also and in your presentation, your masterclass. How would you position statistical entropy, the method that you have proposed, versus current sustainability assessments? Is it possible that at a certain point entropy could discard current sustainability assessments, or how do you see this?
Mm-hmm. I think we need more research, or really to see if there is, how close is the connex between toxicity and entropy. I mean, what I showed here is just an indication, and I had never the time, or I don't know, or the people who were really interested in going into these toxicity details. But it's more a belly feeling that I have that this could be fruitful, yeah. Mm-hmm. If entropy is then so far elaborated that it can really replace other indicators, in my opinion, we should be happy if we have plenty of indicators, because if they point into the same direction, then we can be sure that we don't make any mistakes. So I have no problem with having several indicators. The problem is if these indicators point into different directions, then you have a problem. But if they are rather robust and reliable, I see it's just an addition to an existing set of different indicators. Maybe, I hope, and I think it's a strong indicator, yeah. But I'm always pro that we should use several indicators to be sure that we don't make the wrong decisions.
Okay. Someone else from the room? Yes.
Thank you. Very interesting masterclass. I was really interested, and it's a very strange coincidence. But after this masterclass, I have to give courses to my medical students, and the topic of today is mass balance in the human body. I'm not joking about it. So I'm going to use some of your information to my students. It was very interesting. I was just wondering, do you do some research or maybe some collaborating groups about entropy in a human body or in an animal body, or is it only on a population-based body or mechanical-based, or do you? I don't know if there is some research about entropy in a human body. I don't know.
To make it short, I do not such research. I thought about that because I told you I saw entropy behind everything. But I'm cured now, and I apply to the things where I think that I'm expert in. So it's MFA and it's industrial systems, but I'm quite sure that you could also apply entropy to let's say to developments in the human body. I'm quite sure that our bodies and our living is heavily determined by entropy. Yeah.
Sure. Yeah, I'm convinced of that also. Of course, you have to take into account the metabolism and the anabolism, catabolism. It will be quite some difficult research, but very interesting. Yeah. Okay. Thanks for inspiring us.
Sure.
Well, I see we're almost out of time, unless someone else in the room has a very short question. No, not a short question, Janu? Maybe we have 1 minute left. Maybe very short.
First of all, thank you for the very nice masterclass. It's very inspiring for a young PhD student, as myself. Secondly, you've shown how broadly applicable the entropy assessment metric is, but how broad would you apply it yourself? I mean, as you already have said yourself, I mean, where does the art begin? You've shown it is applicable to agriculture, but as well as to municipal waste management and recycling of plastics. But where would you draw the line yourself? Because I believe it is applicable to almost everything in a certain way.
Yeah, thank you for this question. I didn't really find the red line as long as I'm in the field of anthropogenic metabolism. So as long we are discussing materials, I think the concept is fully valid and has no limits. It's just if it applied to other fields where I see that it has its limits. What I like so much about your work is that you combine it with energy. And this was always a little bit of concern I had when I developed this concept stepwise, because if you consider exergy, for example, you can combine materials and energy, which is considered as a strong advantage of this concept. And I also believed in that. Meanwhile, I think it's an advantage that the statistical entropy does not consider energy. So it's just for materials, and that you combine it with energetic indicators. I think, meanwhile, for me, this is an advantage. So even there, I don't see really limits. Yeah. So I hope you got this impression from my talk. I see a bright future for this concept.
Thank you very much. So I think we can close down the Q&A session now. Thank you very much again.
Okay.
Thank you so much, Professor Rechberger, for your inspiring masterclass. It is now time to confer the honorary degree on Professor Helmut Rechberger. Nominator Professor Peter Billen will deliver the laudation before the official conferral. Afterwards, the honorary doctor gives his own words of thanks.
It is not often that researchers or scientists are at least 2 decades ahead of time. Doing research on the recycling of materials, one quickly imagines, like you saw, that it's not just scarcity or energy that allows to evaluate the intrinsic circularity or sustainability of materials and products. Indeed, if you would have unlimited access to energy, as was demonstrated, everything could be recycled, right? In order to understand materials management, as outlined by Professor Rechberger, one has to master the concept of entropy. And he realized that with our thermodynamic understanding of entropy as engineers and scientists, where we relate it typically to heat, we wouldn't get there. He introduced the use of statistical entropy analysis to materials management, and for nearly 2 decades, as you saw in his reference list, which was clearly only from his group, he was working on this concept and elaborating this concept nearly alone, if I may say. It is now becoming clear by many researchers here in Belgium, but also way beyond and globally, that this was an essential bridge between statistics and information theory and thermodynamics, and that this bridge created an incredibly elegant way of looking at the sustainability of materials and waste management. It is truly telling that Professor Rechberger not only created this highly novel methodology, but clearly has a mission of influencing public policy, companies, while inspiring many students and colleagues and managing a large and welcoming research group. Helmut, I am one of those colleagues who was incredibly inspired by your work. And the framework of circularity of materials that you initiated is helping across the globe to convey the importance of thermodynamic thinking to students. They will have to change the world now in the coming decades. The sheer number of citations to your book on material flow analysis, a staple of the reading list of many starting doctoral students, witness of the enormous impact that your work already had. And I'm very sure that now slowly the scientific community is getting up to speed in understanding and using your groundbreaking work on statistical entropy. I'm confident that your impact will continue to grow. So, for your contributions in improving the sustainability of waste and resource management, and moreover for shaping our view on the societal value of materials, I request that the Rector honor Professor Rechberger with a honorary degree of the University of Antwerp. Thank you.
On the recommendation of the Faculty of Applied Engineering and by decision of the Executive Board, the University of Antwerp confers upon Professor Helmut Rechberger, Professor for Resource Management, Institute for Water Quality and Resource Management, Vienna University of Technology in Austria, the degree of Doctor Honoris Causa in Applied Engineering for his groundbreaking contributions to the development of metrics to evaluate and optimize the sustainability of waste and resource management, and to that end, the establishment of the connection between material flow analysis, classical thermodynamics, and concepts of information theory, facilitating the transition to a circular economy. Dear Professor, dear colleague, by this the epitoga of our university, and also a very special diploma. Congratulations, it is really fantastic.
Thank you very much.
Congratulations also, Madam, to you, because this is also work together, of course. Congratulations to your whole team, to your university, and also congratulations to our faculty represented by the Dean here. We are delighted.
Thank you very much.
Thank you. Okay. Yep. So.
I would like to invite you. Thank you, notes.
Magnificensis, Spectabilas, nominator Peter Biln, dear colleagues and friends, there are quite a few people and institutions I would like to thank, and I thought I will do it in a chronological order. So I start with my parents. It's sad that they cannot be here anymore, but I'm quite sure that they would be very proud of their youngest, and they would be also quite puzzled. So next is my wife, Heidi. I keep it short. Thank you for everything. You are a wonderful person, and everybody who knows you would certainly confirm it. And this brings me to my doctoral father, Professor Emeritus Paul Brunner. Paul, it's a big honor for me that you and Sandra are here today You have been a great teacher and a great mentor and role model, not only for me, but also for a whole generation of PhD students. And you inspired us for the anthropogenic metabolism, and I owe you a lot. Thank you very much. I would also like to thank Professor Tom Gradle, known as the father of industrial ecology, and Professor Peter Pacini, another father of anthropogenic metabolism. They both hosted me during my postdoctoral years at Yale and ETH, and I think it was a big privilege to work together with such excellent scientists, and I learned a lot of them. I would also like to thank my alma mater, the Vienna University of Technology, for providing me an excellent research environment. I have to say I couldn't imagine a better place to work. And would also like to thank my team in Vienna, they are online, for being so supportive and devoted. It's really a wonderful team. And this brings me to the University of Antwerp. I would like to thank you, Peter, as my nominator. Thank you for the laudatio. But a special thanks to that you have established this close collaboration over the past 1 or 2 years. That makes me very happy. So thank you for nominating me for this prestigious award. I thank you, Rector van Gotem, you, Dean Tom Breigelmans, and also the Faculty of Applied Engineering that you approved this nomination. The fact that this honorary degree not only comes from a top university with an excellent international reputation, but also from a university that is located in the center, in the heart of Europe, with all its values and traditions and culture. This means a lot to me, and I will do my best to comply to it. Finally, I would like to thank everybody here in this wonderful room and also the online audience for making this day something very special for me. Thank you very much.
I would like to finish this morning session by saying a few more words of thanks. Thanks again, thank you very much to Professor Helmut Rechberger for your beautiful words of thanks for all the incredible work you are doing, for the extremely interesting masterclass, and of course for accepting our honorary degree. Next to every successful man is a strong woman, so many thanks to Ms. Heide Müller-Rechberger also for being with us this morning. It's chocolate, it's really nice. Thank you to Rector Herman van Goetem, thank you to Dean Tom Breugelmans, nominator Peter Billen, and thank you to the Faculty of Applied Engineering. Finally, of course, I'd also like to thank you for all joining us this morning, you here in this room, and also the people watching online. I hope to see you again in 2023.